to this task. So one every day until Thursday morning. And this is supposed to be mainly for students, but everyone's welcome. So students, feel free to ask any questions. I know it can be intimidating, but these are for you actually. So pretend all the senior faculty are traced out and not here. But I'm sorry? Yeah, we should hide.
Pretend to pay attention. That's good enough.
But we can ask questions as well. But again, the students feel free to participate. It really is for you. And yeah, we have 1 hour. And Joseph, please.
Okay, yeah, thanks very much, William. Yeah, so as William said, so the idea, I think, at the CRM is that in these workshops, we have a lot of wonderful high-level research talks, but there's always a tradition to have like a little mini course, which is more introductory. So again, apologies to the experts. So it's really, really to kind of, make sure that we're all on the same page and revisit some basic things for the sake of students and everybody else as well. So this will be an introduction to quantum criticality, which is probably one of the areas where conformal field theory and many body physics really kind of merge together, which is the theme of this workshop. So in this field, we're interested in quantum phase transitions. Okay, so we all know about ordinary phase transitions, water turning into ice and so on. What's a quantum phase transition? Well, it's a transition that happens at a zero temperature. Okay, so at zero temperature, there are no thermal fluctuations, which are the usual things that will drive transitions. But I guess I'll have to learn how to play with these boards. Come down. Oh, this one you pulled. Okay. Okay. Thank you very much. Great. Okay. And so the setting will be a local lattice Hamiltonian. Okay. We want something that has only two interactions. Otherwise, we can get all kinds of weird things and unphysical things. Physically, interactions will have some finite range in general. So it's a Hamiltonian H of G that will depend on a coupling constant. I have multiple coupling constants, but we'll have one main coupling that will drive the transition. We'll call it G. And will be a many body system. So we'll have n degrees of freedom. So this will be a very large number, let's say on the order of Avogadro's number. And we'll be taking that number we'll be taking it to infinity to get nice sort of mathematical results that can describe key features of systems that are finite, but have a very large number of degrees of freedom. And specifically, we'll focus on continuous quantum phase transitions. Okay, so we can have first order transitions. Of course, they can be interesting physically. They can happen in physical systems, but there's something particularly interesting in these continuous transitions. So these are essentially an avoided level crossing the ground state and some excited state that happens at a critical value of this coupling. G calls GC, and this level crossing, so I'll continue over here, that the avoided crossing becomes sharp in the thermodynamic limit. Okay, where we take this number of degrees of freedom to infinity. Okay, and so what this means is that because of this crossing that becomes sharp, we'll have some non-analyticities in thermodynamic properties, say ground state properties, or thermodynamic properties. For example, the energy density, correlation functions, precisely at this transition point, and these are caused, particularly again, by not thermal fluctuations but quantum fluctuations. Okay, hence the terminology of quantum phase transitions. Okay, so So a typical phase diagram you'll have is, something like this. We'll be tuning our coupling constant. Then this GC will have a transition. This will be this quantum phase transition. And of course, experimentally, we'll always be at some finite temperature. And so what often happens is that, you could have something like this where, you might have a thermal phase transition, okay, which will be a classical phase transition. Always, because you could be, for example, below the lower critical dimension of the system. And so maybe you cannot have, let's say, order at finite temperatures, but so in many cases you'll have something like this. Okay, and so where's the eraser? Here. Thank you. All right, so that's the sort of general idea, but as always, it's good to make these things concrete. And so to really get a sense of what these transitions are about, we like to work with certain toy models that we can solve and can give us a good sense of what these ideas mean concretely. So we'll be looking at what maybe we could call the hydrogen atom, in quotes, of quantum phase transitions, okay, which is the one-dimensional transverse field Ising model. Okay, you could say the one-dimensional quantumizing model. So I'll use this abbreviation TFIM. Model is very simple to write. Okay, will be a function of two couplings, some coupling J and some coupling H. So it's an Ising model. So we have a nearest neighbor interaction. We'll have a chain of n sites and spins. I'll draw this in a minute. We'll have an interaction between neighboring spins on this lattice, the Z component. And then, so if I only have the first term, this would be, the classical Ising model that you will study, in some course in classical statistical mechanics. But then we'll add a field here, okay? But to the difference of, the sort of probe field you might add to the Ising model, the classical Ising model, the field is in the x direction, right? Although the interaction is in the z direction. And so this term now does not commute with the first term, so it's truly a quantum mechanical Hamiltonian, and without loss of generality, we'll pick these two couplings to be positive. Okay, so this model has a symmetry. So Z2 spin flip symmetry, okay, which it's a global symmetry, so it amounts to flipping, reversing all these spins in z direction for all sites. And it's generated by an operator, okay, which is simply the product of these sigma x spin flip operators on all the sites. Okay, so the model has a global symmetry, and want to see what happens as we vary these couplings. Okay, so again, just to draw things, we'll have a chain of n sites. Okay, and actually, okay, so 1, 2, 3, so on, and then we have, some sort of localized magnetic moments on these sites, and I'll try to be careful here. Actually, consideration of boundary conditions is important to get the physics right, and so here I'll be considering this open boundary condition. And it's not just a toy model, has been realized in various materials. Perhaps the cleanest demonstration of this is in this cobalt niobium oxygen compound. So this is some nice work by Radu Kuldea at Oxford. This was published in Science in 2010. Okay, so the basic idea is that you might think, interactions between spins are in general isotropic, but if you have spin orbit coupling, for example, you can have anisotropy in the space of couplings, and you can have this sort of Ising-like anisotropy in your magnetic Hamiltonian. So, as always, to understand phases of a Hamiltonian, it's good to look at limits in the space of couplings. So we'll look at, there's only one parameter really at zero temperature, which is a ratio of these couplings. So we'll be looking at first the limit that J is much greater than H. So in this case, our Hamiltonian, we can drop this transverse field, and we have a sum of these bond interactions. So we reduce to the classical 1D Ising model, and so we know what happens in this case. Classical 1D model. So we know that the model does not order at any finite temperature. It's always disordered, but at zero temperatures, you have order. So the model orders, ferromagnetically at t equals 0. We can minimize all these terms, and so we have two degenerate ground states. Okay, so we have two degenerate states where all our spins can point either up or they can all point down. Okay, so we have these two ground states. We can distinguish them by a ferromagnetic order parameter. The m is 1 over n, sum over I 1 to n of this expectation value of this z component of spin, and so this has a well-defined value in the thermodynamic limit. Okay, so in these ground states, it's 1 or minus 1, and since they're degenerate, if we turn on a small symmetry breaking field, we'll have a spontaneous breaking of this Z2 spin flip symmetry. Okay, so if I had chosen, let's say, the J coupling to be negative, for example, then would have anti-ferromagnetic order, but again, we'd have two degenerate ground states, and the magnetization we will be looking at the staggered magnetization as the order parameter. Okay, so this is very well. This is well and good. This is the large J limit. We look at the opposite limit where the dominant coupling is this transverse field. Then again, the Hamiltonian simplifies. We can just look at this transverse field term. Okay, so this is even simpler because again, all the terms in Hamiltonian commute with each other, and we just have a Zeeman field, a uniform Zeeman field, and the x direction. Okay, so it's very obvious what happens. All the spins want to line up with this x direction. So the ground state is a very simple product state. So it's a unique state with all the spins in the, let's say, positive x direction. So that's the ground state wave function in this infinite h limit. And again, we can ask what's the order parameter. So expectation value of sigma z in a sigma x eigenstate is 0. So the magnetization is 0. And even though it's a very simple model, the physics is actually interesting. We have a quantum from the point of view of the magnetism. This is interesting. It's a quantum disordered paramagnet. Okay, so it's really a spin liquid. It comes matter parlance. Okay, because you don't agree with that? I thought it was a spin liquid.
I mean, it's a trivial.
It's a quantum disordered. Well, it's a 1D spin liquid.
I think usually quantum spin liquid explicitly like.
Oh, the rules out the D equals 1?
Exclude the
Paramagnet.
sort of paradigm.
Oh,
I mean, that, so you want something, spin liquid should have something along with the wave function should not be any of that.
It's a product stage.
fair enough. Fair enough.
Product stage.
It's in 1D.
The-
No,
It's a product stage, yeah.
not a spin liquid.
Not a spin liquid. Actually, you can write not a spin liquid.
Not a spin liquid. Oh, man.
Because
All right.
you don't have any spin on like the.
I know. Yeah,
Which happens in-
I meant in the, the old sense of the term, right? No magnetic order down to 0 temperature.
Yeah, it's a modern lecture. Yeah.
Like an experimentalist would, someone who doesn't know these,
We shouldn't trust them.
no, all right. Fair enough. So, in case we have magnetic order, that is destroyed by quantum fluctuations. That much we agree on. Good, people are paying attention. Okay, so we have these two extremes, and so clearly there's something pretty dramatic that must happen between these two ground states. We cannot adiabatically go from one to the other, so there should be a quantum phase transition at some critical value of this, again, this unique coupling, okay, which is G, and I'll define it as H over J. Okay, so a very small G, then we are in this trivial paramagnet ground state, and at, sorry, large G, we're in this paramagnetic state, and then small G, we are in the ordered state. Okay, so it turns out we could actually solve this model exactly, and we'll get to that in a bit. But before we do that, we can already get some insight about this phase transition, in particular, where at what value of G it is, by invoking something called Kramers-Wannier. Yeah, and please interrupt at any time with questions, comments, and so on. Okay, so so what we'll do in this case is we'll again write down our or draw our Ising chain. Let's see, I guess we don't have colored chalk here. Oh yes, I think there's some here. Okay, so we will okay, so we have our spins that are defined on the sides of this chain, and what we'll do is we'll, so this is the lattice, and then we'll introduce a dual lattice whose sites will be basically at the midpoints in between these sides of our lattice. Okay, so I'll call this a dual lattice. Okay, so for any site I, there will be a dual lattice site at I plus 1/2. And so this, okay, so we'll define what we'll call dual spins. Okay, that'll define as follows. So we'll use the letter mu for these dual spins. So the x component of the dual spin, that's I plus 1/2, we'll define it as the product of sigma z on the two sites that are on either side of this dual site. Okay, so we'll do that. Again, I'll be careful here with the counting. It will turn out to be important to get the right physics once again. And so this operator, so is this energy density on the bond, and you can think of it as a domain wall measuring operator. Okay, because its value is -1 if there exists a domain wall between those two sites, and +1 otherwise. Okay, so we'll measure these domain walls, and then so this is the x component, the dual spin, and then we will define a z component as follows. So so will be a, for now they're just labels. Okay, obviously suggests that this is going to be a conjugate operator, but that's something we'll have to check. Okay, for now I'll just define it. In fact, mu z, I'll define it implicitly as a kind of sort of reverse of that. So I'll define it in two steps. So first I'll define the first z dual spin, the one right here, explicitly as sigma 1x, and then for all the other ones, I'll define them implicitly via this equation. Sigma ix is the product of the mu's. Okay, mu I plus mu minus 1/2 mu I plus 1/2 for I goes from 2 to n-1. Okay, so we can do that, but what I would like to have rather is an explicit expression for these operators. Before I get to that, I just want to observe that, okay, there's a match between the number of operators. So I've defined n-1 of these because we had n-1 bonds, and here likewise there's 1 here, and then there's n-2 here. So I do have n-1 operators also. Okay, so I have the same number of mu x and mu z operators. Okay, so if I just said, maybe I want to keep this. So I would rather have an explicit expression. So I can actually solve, solve this equation by essentially a kind of non-local product of operators. Okay, so I'll write this down and then it's something one can check. So it'll be the product of all these sigma x operators. Okay, so I'll write this. So product of J1 to I of sigma J x. So it's the okay, so again, I can define this or I can write this down. I can check actually that this solves this equation for all these values of I. Okay, because if you multiply this string and the same string shifted by 1, then there's a bunch of products of sigma x that appear twice, the L squared to 1, and then I'm left with 1 sigma ix. So this is what you would call a string operator. Okay, so non-local operator on a finite infinite system, it would have an infinite number of operators. It flips all spins to the left of the dual site I plus a half. So okay, so if this one was a domain wall measuring operator, then this is a domain wall creation operator. All right, very good. So I've said that I gave them suggestive names, u, z, and x, but that they are really conjugate operators. But since this is a course, I can give exercises and avoid showing things. So as an exercise, you can check for yourself that these operators actually anti-commute on the same site and commute on different sites. Okay, so you can show that mu z I plus 1 and mu x I prime plus 1 anti-commute for I equals I prime and commute I different from I prime. Okay, so it's not that hard to show. Essentially what you'll have is either you sort of get rid of an even number of these sigma x's, or there's one that's left over, and therefore you can show that they obey the same algebra as the original sigma spins, and therefore we're at least justified in calling them dual spins, okay, even though we don't yet know what they're good for. Okay, so we can just define that. The use, of course, of these operators is that we can rewrite the Hamiltonian in terms of these new degrees of freedom and make an interesting observation. Okay, so we can write the transverse-field Ising Hamiltonian in terms of these dual spins as follows. So we have an operator that is just exactly the bond interaction term, and so this the sum over Ising interactions in this dual language just becomes a sum of mu x terms with coupling minus j. Okay, for 1 to n minus 1 mu I plus a half x, and then for the transverse field, I guess I've erased it, but we found this. Yeah, that's right. So then remember that I defined this mu z implicitly by a product, and so now this sigma x term becomes a product of mu z's, except for the first term. Okay, so remember that sigma 1x was equal to a single mu here. I'll write it out specifically, and then for all the other ones, 2 to the n minus 1, we have mu z I minus a half, mu zi plus a half. And again, if you're paying close attention, I only define them for up to n minus 1. But okay, so there's still a sigma n here x that is unaccounted for. Okay, so to remedy this sort of asymmetry here, we want to write everything in terms of the dual spins. So we'll define finally a mu n plus a half. Okay, so remember that I had my lattice like this, and I had my dual spins here. Well, this amounts to adding an extra, sort of fake dual lattice site here at the outside of the lattice, and I'll define this as a product of all the spins, all the sigma x's, and product of all the original x spins. So this is nothing but the generator of the global symmetry. Is this global spin flip operator? Okay, and so it commutes with the Hamiltonian. Okay, so all right, so therefore, so having defined this extra mu z, now we can write into sigma x n as a product of this one and the one immediately preceding. So this is mu of n minus 1 plus a half, and then this new guy n plus a half, and therefore now we can absorb this last term here in the sum. Okay, to write the Hamiltonian in this form. So first I'll write the minus h couplings first, and I'll put the 3/2 term at the end. So we'll have I 2 to the n, I minus a half, I plus a half, minus j, I n minus 1, mu I plus a half x, and then this lone mu 3/2 z. Okay, so yeah, just to shift term into sum. So I have I to the n minus 1, mu I plus a half z, mu I plus 1 plus a half z, minus j 1 to n minus 1 plus a half x, and again minus. Okay, so what do you observe? Well, this looks very much like the same model we started with. Okay, so this is again the transverse-field Ising model, but we've exchanged the couplings. Okay, so what used to be J now seems to play the role of H, and vice versa. Okay, and also with one less site. Okay, so in the thermodynamic limit, of course, it doesn't matter, but again, to see everything right, it's good to keep track of all the terms. So this is what is called Kramers-Wannier duality in the language of the classical Ising model. So by Kramers-Wannier in 1941. So it's a little bit more cumbersome. It's sort of easier to do it in the quantum problem. But the basic idea is that perform a duality, which is essentially a non-local change of variables in general. Okay, so in the quantum problem, we went from these sigma spins to these mu spins. Okay, so you can think of this as a non-local unitary transformation. And what it does is that it maps the 1D transverse-field Ising model to itself. Okay, so it's another model of the same form, but with different couplings. So this is what we would call the self-duality. Yeah, so but with couplings interchange. Okay, so what that means is that if we look at these two different regimes that we looked at in the beginning, so for example, the J much bigger than H, limit, if we go to the dual model, then if we look at this ratio of J dual, the dual exchange coupling over the dual transverse field, actually now this becomes H over J, and now this is much less than 1. Okay, and vice versa. So you can think of this as a strong weak duality. Okay, so if you think of the G, the ratio of them is your coupling constant, then you map a strongly coupled problem to a weakly coupled problem, and vice versa. So that's the duality. Before we go to the critical coupling, it's instructive to understand the phases of our model, but now from this dual point of view, okay? From the dual spin perspective. And the dual spin perspective is really a domain wall perspective, okay? So as I mentioned, we had these domain wall measuring operators and these domain wall creation operators. And so clearly what we're dealing with now is the description in terms of domain walls. Okay, so again, right, we'll be looking at these limits. So first, if I look at the limit H over J goes to infinity, this is the limit where so instead of writing dual, I'll write them with a tilde, these dual couplings. Okay, and so in this limit, the dual Hamiltonian, okay, I don't have it here, but essentially what we'll get rid of now is this H dual term. So we don't have the transverse field, we just have the interaction term. Okay, which with these mu z's, I plus a half, I plus 1, plus a half. Okay, and crucially, we have this little extra term here. And so now this is a classical problem. All the terms commute with each other. We can minimize everything independently. And in particular here, okay, we can minimize this one. Obviously, this 3/2 site, wants to be in the +1 direction because of this Zeeman term. So this one is set, and then let's look at the remaining terms. So if I write them out explicitly, then okay, so this equality for the Hamiltonian, then I have minus h, and then this starts off at 3/2, 5/2, 7/2, etc., all the way to so we'll okay. Yes, minus a half, plus a half. Okay, and you see that because this one is polarized, then necessarily this term wants the 5/2 spin to also be in the +1 direction. So this term makes the 5/2 spin to be +1. Now that 5/2 is +1, this term makes the 7/2 spin be +1, so on and so forth. It propagates, all the way to the last one, which is mu z, and plus a half equals +1. Okay, so it's a very simple ground state. All these mu z spins are polarized in the +1 direction, and so okay, all of them. So we have a unique ground state, and so you see why it's important to keep this term, because otherwise you would have a ferromagnet if you only have this term, and then it's not clear. You would have a degenerate ground state, but you want to have a unique ground state because you are dual to the paramagnetic, the trivial paramagnet. So you can think of this as a ferromagnet, in a field, in a small field that lives on the first site of the dual lattice. Okay, so therefore, okay, so we have this sort of ground state wave function in the dual picture, so it's very easy to compute, order parameters, and so we see that this trivial paramagnet, okay, which obtained in the limit that we're considering H much bigger than J. So this had expectation value of the original spin to be 0. Now, okay, so again, this was the order parameter. So now this is dual to what we typically call a condensate of domain walls, okay, where now this guy, this mu plus a half is non-zero. Okay, so remember that this was the, this mu z was a domain wall creation operator. So that's why we can think of this as a condensate of domain walls. And so in general, these types of operators, that acquire an expectation value in a phase that, in the original language is disordered, is a disorder operator. Okay, but again, notice that there's no symmetry breaking in this phase. So one more thing. So we want to check that we have all the right properties of the paramagnetic phase. So we have a unique ground state, that's good. And also we want to check that we have an unbroken Z2 symmetry. And again, this follows from this because note that this, this sort of extra fake degree of freedom at the outside of the lattice, mu n plus a half, this was really the global Z2 symmetry operator. Okay, remember, it was the product of all the sigma x spins. The symmetry generator here, notice that it's equal to 1, and they're on the ground state, okay, in the ground state. So therefore, if I act with this operator on the ground state, I guess plus 1. And so clearly, I know the ground state is invariant under the Z2 symmetry. So we have an unbroken symmetry. Okay, so ground state invariant under the Z2 symmetry transformation. So there's no spontaneous symmetry breaking. Good. So we understand this limit, the trivial paramagnet, and then we can look at the other limit, which is J, where H goes to infinity. Okay, which now maps to the sort of weak coupling limit, or if you will, this is the weak coupling limit in the original language. Now this is the strong coupling limit in the dual picture. Again, that's fairly simple. So what was in ordered state in the original language with the sort of classical Ising model now maps onto a pure Zeeman term for the dual spins. Okay, so very simple. It's a polarized state in the mu x direction. So it would be a again the polarized state of these mu x variables. So 3/2, 5/2, and this goes all the way to n minus a half. So again, there's a bit of a paradox because this suggests a unique ground state, but again, the physical problem has a ground state degeneracy. It's in symmetry broken phase. So how can we see the two degenerate ferromagnetic ground states? The original picture. So again, we can see this by accounting for all the degrees of freedom in our open boundary condition description. So remember that we have defined, recall we have defined operator on this fake lattice site, mu n plus 1. Okay. And so it's important to have the same number of degrees of freedom in the original and dual formulations. Okay, and then it's good. I'll basically conclude with this. Okay, so the Hilbert space dimensions must match. Okay, so the H and the sort of H dual Hilbert spaces must each have 2 to the n dimension. But the Hamiltonian itself this dual Hamiltonian, it only acts on, 3/2, 5/2, and all the way to n minus a half. Okay, and so this operator, or the mu x n minus a half, spin does not feature in the Hamiltonian. Okay, so there's therefore that operator commutes with the Hamiltonian, but it's a valid degree of freedom, so it's a zero mode, and it can be either up or down. Wave function was incomplete. There's one more site I needed to write. So this H tilde commutes with mu n plus a half z, and so we have two degenerate ground states, if you want. They're mostly paramagnetic in a sense. They're polarized, but this last degree of freedom can be up or down without changing the energy. Okay, so that's the n minus a half, but then we have the n plus a half. So we have this one, and then we have this one. And the last side can be down. Okay, so we do correctly have two ground states. We have all the right physics. We can describe the two phases in the original language, the dual language. And so what we find is that this Kramers-Wannier transformation or duality interchanges the paramagnetic and ferromagnetic phases. Okay, and clearly that means that the quantum phase transition, where we have neither one phase nor the other, must be at the self-dual point of this transformation. So since the transformation exchanges J and H, then at the self-dual point, we have H is H tilde equals J. Equivalently, J equals J tilde equals H. And so the critical point is at GC, H over J critical equals 1. Okay, so also, you can work with the original Kramers-Wannier transformation on the 2D classicalizing model. There's this nice equation for TC, and then you look at this in this extreme anisotropic limit when you go to the tab continuum limit, and you see that everything agrees in that limit. Okay, so it's good. So I'll stop here, and then next time we'll actually show that we can go beyond this. We can actually solve the entire transverse-field Ising model by combining these order and disorder operators and get the right degrees of freedom throughout the entire phase diagram. Any questions?
Well, I had a question from the very beginning, discussion when you mentioned got the analogy of the band costing, the violent band costing, and then there's an excited state, there's a down state, and I'm wondering how does that discussion work in gapless compressible.
Well, I think there's still some energy scale, right? That there must be some energy scale that goes to 0 at the critical point. It could also be things like if you have, for example, breaking of let's say a No2 model, for example, right? So you can have, well, let's see, that would be a finite temperature. But yeah, no, I think it's still an avoided level crossing between many body ground state and excited state that goes to 0.
Finite system or?
Right, you need to be in the thermodynamic limit to see this physics happening.
Statement then
there will be some non-analyticity that will be present in the.
So the ground state and the excited state is of the O2 or ON model and a symmetric working place. With that the exact excitation, that wouldn't be the case, right? Because the excited state is touching the front.
But there will be some the trivial paramagnetic phase will be some gap phase, right? And so this gap will go to 0 as you go to the critical point. Yeah.
And then could you just use the argument to say that if you have gapless states on both sides of the theory, let's say constant gapless one is going to be then something like an ordered state, would this then naturally not fall?
Yeah, so right. So in that case, I would say, so certainly, in finite size, you will see that this gap scales differently on either side of the transition, right? Because On the one side, you'll have sort of a kind of tower states coming from symmetry breaking. In the other case, you'll have, let's say some gapless spin-off spectrum. So there will still be some qualitative difference between the scaling of the gap in finite size. At least that would be one diagnostic that would tell you that something different is happening. Oh, I think Julie had a question. Yeah.
So I was just wondering, how does this argument and this duality work with parity boundary conditions? I guess in that case, some of these. Will you comment on that?
Yeah, that's interesting. So it's a bit of the story is a bit more complicated, and so in that case, the proper way to do this is to actually see. In that case, the Ising model really becomes like a gauge theory. So then there's a description you can write down that involves simultaneously it's like an intermediate step. So you can write down the order variables, the disorder variables together, and you'll see that there's a gauge symmetry that emerges. And one thing, for example, will be that this is Z2, this global Z2 symmetry gets mapped onto a flux, like a Wilson loop observable in this picture, which can be either a 0 or pi. So it's a little bit more complicated. So in other words, there's there could be if you look at periodic boundary conditions to capture all the sectors of the Ising model, you need to look at sort of both periodic and anti-periodic sectors, and that becomes a dynamical variable. So there's you can make there's a very explicit discussion you can do. It becomes a little bit more involved in the counting of degrees of freedom. But yeah, so the best way to actually do this is to view this Ising model as a gauge theory, actually, even in 1+1 dimension. Yeah, but yeah, it's an interesting story.
So is there a general way to spot a duality if we given a new model?
Good question. I don't think so. I think it's usually, that it's a stroke of genius in a sense, right? That to see these things happening. So I mean, I think now there's a bit of intuition, right? We try things, right? So for example, there's a notion of, okay, that's a classic sort of example. You try to look for something that might condense in a disordered phase, right? Try to look for something like a disordered field. It will typically be some sort of non-local thing. Once we get to the mapping, the exact solution, then you find that the right degrees of freedom are a product of an ordered field and a disordered field. So this generalizes in the sense that there's some sort of you bind an excitation with a topological defect, right? So here we'll bind like a spin flip to a domain wall. So in hard dimensions, you might bind a particle with a flux, a vortex, or 3 dimensions, you might bind a particle with a monopole. So you'll try to bind some particle excitation, some kind of trivial local excitation with something that is like a topological defect. And in some cases, yes, then this turns out to give you a good dual description. But I'm not aware that there's a general way to discover these dual transformations. They're quite non-trivial, right? And they're sort of yeah. So I think it's a case by case.
Fine-tuned, right?
What's that?
This model is fine-tuned. There's infinite symmetry.
Yeah, that's right. So if you perturb this model, by various other terms, in a sense that you'll still have the two phases, but the duality mapping won't hold, right? That's right. That's a very nice model that sort of in which you can do that very explicitly, which is quite rare. That's why it's a nice toy model, but not necessarily representative of generic quantification conditions.
Yeah, just to add to that. So here, the ferromagnet is mapped to the ferromagnetic phase and so on. And to get the correct number of ground states on both sides, you have to do the duality on the lattice.
Right.
On a finite chain. But if you do that, for instance, on an infinite chain, open chain, or even the continuum, so the statement is essentially that self-dual, pi-pole theory, take map pi-pole theory. And if you do it in the continuum, so how would you make sure? I guess you could sort of put in a Z2 gauge field on the other side to make sure that you only have a unique ground state on the right, when you're in the domain wall theory. But short of doing it by hand to make sure, putting in a dynamical Z2 gauge field to make sure that there's no continuous symmetry breaking or anything like that. Could you sort of derive it just from because you could do some sort of log spin RD and derive the continuum theory in the domain wall side?
I'm not sure. I know that people, for example, will write these continuum theories that have a topological term, right? So they will write down, for example, just the 5-4 theory in 1+1 dimension, and then add some topological term, there would be some gauge field and some topological term that captures the right physics. But to my knowledge, these are sort of, we know what happens and then we write down something that captures those effects.
You do it by hand.
You start from the lattice, right? So one starts from these exact dualities where everything is controlled on the lattice, and then you sort of write down the corresponding, topological terms and so on. But I don't know if you can sort of directly derive it from the
Microscopic.
continuum. Yeah, I know maybe in Chen knows, right? I think it's typically something that that's why it's such a precious example, right? Because everything can be worked out very explicitly. In general, yeah, I think you can write down topological terms that will affect these various sort of flux attachments and all these things. These are very non-perturbative things, right? So coarse graining is unlikely, sort of RG is not going to capture these things, at least not natively done. So it's quite special, I would say. Questions, William?
Well, maybe not a question, but do you have like any good references the students can read for like the next lecture, or
Yeah. So the next, I mean, I can't reveal my sources. That's no. This is stolen from John McGreevy's the quantum field theory lecture notes, which are beautiful, in my opinion. And there's more detail. For example, the periodic boundary condition stuff. If you're interested, you can look that up. In there is discussed. Also, R. Shankar's book on quantum field theory and Kinnis matter, field theory and Kinnis matter. It's a relatively recent book. He also discusses that. Yeah, so next time I'll do the Jordan-Wigner transformation. It'll be very explicit. I'll do it like that. And then afterwards, I'll do sort of Landau-Ginzburg theory and some basic RG. But yeah, feel free to accost me and ask questions. Andrea?
There is an historical, very nice review, John Colwood, Review of Modern Physics, 1974.
Yes, lattice gauge theory and spin systems.
I think still very good.
That's right. Yeah, for explicit lattice dualities in higher dimensions, for example, you can do like lattice gauge theory in 2+1 dimension to the Ising model. Yeah, so that's very nice. Yeah, that's a beautiful reference. I agree.
Also, Savit.
Right, Robert Savit. Yeah, RMP, right?
SMP of the Review of Modern
81 or something. That's right, or 80. Yeah, very nice for lattice dualities in statistical mechanics quite generally. Yeah. Great references. And Polyakov's book also. That's a very nice book. Okay, so I guess we'll stop here, right?
I think you'll
Yeah, sure.